Okay, so thank you very much. So thanks all for being here. I'm sorry that I'm not here, or I'm here, but I'm not physically like with you. But big thanks to the organizer for making this exception, for enabling me to present this talk today virtually with you. So I'm gonna talk today about our paper, Deep Policy Dynamic Programming for Vehicle Routing Problems, and this is joint work with my collaborators. So this is Herke van Hoof, Joaquim Gromicho, and Max Edding. Um, and so in general, I like to start my presentation introducing my favorite problem actually, and this is what I call the traveling scientist problem. So imagine, let's say you're at a conference. I think this is not so hard for you to imagine at this moment, but imagine this is a conference, right? Like maybe ICML or NERDS, where there's like a big poster session, and you picked some posters that you want to visit, right? But in order to have time actually to look at this post, right, you want to minimize the time you spend walking around to all these different posters, or in general, let's say locations. So the question is, what is like the optimal order in which you can visit all these different posters to minimize, let's say, the total time you spend walking around? And surely you want to get back to where you started. Typically, it's the coffee corner. And so this is the traveling scientist problem, as I call it, TSP, may look familiar to you. And indeed, this is a very difficult problem because in general, it's NP hard. And so what does that mean? It means that if we want to, let's say, have an algorithm that can find the optimal solution for any given problem instance of this problem, then we have no hopes basically of finding an efficient algorithm. But fortunately, this is not what we want to do typically in practice, because in practice, usually we care about finding, let's say, acceptable or reasonable, good quality solutions for maybe a relevant subset of problem instances only. And this is quite feasible actually. And so the way we do that is that we use heuristics. And so the way I like to think of heuristics is as rules of thumb. So for example, if you're going to solve a routing problem or like TSP problem, then one such heuristic would be like the next location I'm going to visit, it should be nearby, right? I shouldn't wander around, go back and forth all the time. But this development of heuristics, that's like a costly, and that's like quite difficult. So what do we do nowadays, or in the past few years, we've seen this direction of research coming up, is that we use deep learning algorithms, basically machine learning, deep learning, to learn these heuristics by themselves. And so my first try actually at this approach was already a few years back. And so there was this paper where we used a model, which is basically a transformer model, to predict in a routing problem, let's say, where to go next. So this you could see as parameterizing a construction heuristic, which could really construct a route for a TSP problem or for a vehicle routing problem, like one step at a time, just predicting, giving the partial solution, where should I go next? And this doesn't produce state-of-the-art results, but I would say it's quite reasonable and it's quite impressive actually, given that it like constructs this solution in order without any like local search. You can get reasonable solutions for like different types of problems. We actually tested this on. And so this was already a few years back, so a lot of people actually followed up on this work. New methods were developed, and one thing that I was particularly enthusiastic about was this work by Josie and collaborators, and they actually used a different model. So the model I used a few years ago was like an autoregressive model, we call it. So it predicts like one step at a time. They said, let's just consider like a traveling salesman or TSP instance as a graph, a fully connected graph. And we're just going to use a graph neural network, which in a single pass is going to predict for each edge in this graph, like what is the probability that this edge should be part of the optimal solution. And the result, then what you get is basically a heat map of edges which indicate which are the most promising edges. And then we could use that in a simple beam search algorithm, which would then yield a feasible tour or feasible solution to the problem. And this is interesting for two reasons, because it's computationally actually more efficient, because you can just make all these predictions at once, let's say in parallel, whereas the previous approach was very much sequential. which you would say it means the model is much less expressive, but actually it also yields better results. So this really got me enthusiastic. But I think there's one thing which we can do better, and that is the beam search aspect, because that's just not the best way, I think, to convert this very valuable heat map of promising edges into a solution. And that brings us basically to the paper I'm presenting today, which is deep policy dynamic programming. So this uses a dynamic programming algorithm combined with this beam search. So if you decide to only like pay attention for 5 minutes, let's say, this is the short summary. So deep policy dynamic programming, it's a flexible framework actually for vehicle routing problems, and it restricts a dynamic program to promising parts of the state space. So it guides this dynamic programming algorithm, and it does so by using this heat map of promising edges, which is predicted by a neural network. And I want to take the opportunity for a small side note. So if you like this research direction of, let's say, neural vehicle routing, as I like to call it, then I can highly recommend this blog post, which is also by the author of the model I just presented, which nicely summarizes all the different approaches which have been taken in the past few years. And then after you've done that, if you want to bring this into practice, I invite you very much to join actually our NURBS competition for this year, which we are organizing, which is on vehicle routing problems, where we try to bring together basically research from operations research, especially in the vehicle routing community, with research from machine learning community to actually work on the same problem. And this is a static and a dynamic variant of a vehicle routing problem with time windows. So if you're interested, please check it out. Okay, and so that said, let's move on to the technical part. And so I want to start with introducing you the classic dynamic programming algorithm for the TSP. So this may look familiar for well, some of you or maybe most of you, but this is a very nice formula that actually captures the dynamic programming algorithm for the traveling salesman problem, traveling scientist problem. Abbreviation is the same. And so what this formula expresses is how we can compute basically the cost of a partial solution for a TSP. So if you consider a subset of the node, which we call S, and we say if we started at, let's say, node 0, and if we want to end at the current node I in this subset S, then the cost of this solution, we can basically express that in terms of the cost of smaller solutions. And so this combination of a set of nodes that we have visited and the node where we currently are, this is what we call the dynamic programming state. And then this cost, it expressed the minimum cost actually to go from node 0 to the current node, visiting all these nodes in this set. And we can basically recursively express that as that we need to choose basically which is the previous node we came from. We should have the optimal cost, so that is this part to this previous node, and then add, of course, the cost to move from this previous node to the current node. And what we then see is that this minimization is doing, it's actually for each dynamic programming state, so for each set of visited nodes and the current nodes, it's selecting the best solution. So it's only considering the best solution. So for example, here, if we have the state where we consider these 4 nodes, and we are currently at node the third node, then there are 2 options that we can have in this case. In general, it can be more, but here it's 2. And we can actually see that the left option, it's the shorter solution than the right option, and any possible way to complete this route, or here there's only one obvious way, but in any way I could complete this route, I could complete this route the same way, and so this will always yield a better solution. So what we say is that this right solution is dominated. So that's the dynamic programming principle, and through this minimization, we then just ignore this solution basically in our search, and this allows us to drastically reduce our search space. And so by viewing it in this way, we can actually compare a dynamic programming algorithm actually with a brute force algorithm. So if we would implement a brute force algorithm for a TSP problem, then we would maybe just start with an empty solution at the root, the root of a tree, which represents all possible solutions. Then we would just look at all possible ways to extend the solution into a solution of length 1, then all possible ways to extend the solution again, etc., etc. And we get basically this factorially sized tree, which represents all possible permutations in which I can visit a number of nodes. So that's the brute force approach, and that's the forward view. You could say you always start with an empty solution, whereas if we go and look back at this formula, this is actually a backward view of the problem. So we express the cost for a certain subproblem in terms of the cost for a smaller subproblem. So we can indicate it like this, and there you see that it's not a tree, it's actually a directed graph, because like the same subproblems you occur in different subproblems again. And so this reduces then the complexity from factorial, let's say, to exponential, because there's just a lot of less states than there is solutions, because many solutions correspond to the same dynamic programming state, and you only have to consider the best solution for each state. And so this forward view and this backward view, they may seem different, but actually we can just align those two views. And this really makes it clear that also if we think about how can we implement such a dynamic program, that what we can actually do is just implement, let's say, a brute force algorithm, which operates in a breadth first manner, but then in every iteration, so first we consider all solutions of size 1, then all solutions of size 2, we're just going to remove all dominated solutions, and so this then gives us our implementation of our dynamic program. And so, like I said, in terms of complexity, this is much more efficient because it moves from like factorial to exponential complexity. But unfortunately, this is still impractical. So it's much and much better, but still we can only do this up to a limit of, let's say, 30 nodes or so. And so what can we do on top in practice? That is just heuristically reducing the search space. So just cut parts of the search space. And if we do that for a brute force algorithm, then what we get, for example, is a beam search. So in beam search, we would not consider all possible expansions, but let's say only the top 4 in this example. So we would start with one empty solution. We would maybe generate 4 extensions, and at a certain point we get more and more solutions, but we only keep let's say the 4 best ones, and we continue with that. So that's a beam search, and that then has a linear complexity in terms of the length of the solution, and it's constant if you fix like this number of solutions that you consider. And so we can do the same thing basically for the dynamic program. So we can also restrict our search space. So if we build this in iterations, we build our solutions, but we remove our dominated solutions such that we have a dynamic program, we can still decide to only continue with, let's say, the top 4 solution. And so this paradigm is known as restricted dynamic programming. And so that also gives this nice complexity. But of course, the question is, how do we select which of these solutions that we keep on what we then generally call the beam of the search? And to do that, we need a good policy, which then decides like which part of the search space that we actually consider. And what deep policy dynamic programming do, or what we propose in this paper, is to actually use a neural network or use this heat map of predictions to do that. And so how then the overall algorithm works is that we just start with a single solution, right? And then in iterations, we're going to expand this solution. So add 1 node to the solution, then we're going to remove all the dominated solutions, and then we're going to use this policy to select the best B, in this case 4 solutions, and we're going to repeat that until we have a complete solution. And then very importantly, the question, like, what does this policy then look like? And this policy, it selects basically the top solutions that maximize what we defined as the score of the solution. And the score actually consists of two components, which are the heat and what we call the potential. And so the heat is basically just the sum of the heat values. So these are values between 0 and 1, which indicate for each edge like the probability that they're part of an optimal solution according to the neural network. So this heat map, this is predicted by the neural network. And so we're going to add the heat of the edges in the solution. But then also we're going to add the potential, which is sort of an estimate of the heat that we can still get based on all the remaining nodes that we didn't visit yet. So if we look at an example, so let's say this is a partial solution and we want to have a score. So we want to have an estimate of what is the quality, let's say, or how desirable is this partial solution in the context of our dynamic program. Then what we can do is just add up all these heat values in this partial solution, and as you can see, they are quite good edges, so this will give you a quite good score. But obviously this is not a very good partial solution, because if you make this solution, you skip over some nodes, so you're going to have to incur a large cost later. So to take that into account, we also add this potential, and in this case the potential for these two nodes will be lower because of a lot of edges which before were still possible, which had a high heat value. They become impossible as soon as I take this path, let's say. So by taking into account this potential that some edges become infeasible, you can already know that this is not going to be a good solution. So this avoids this obvious problem of skipping of nodes. So this is quite a general concept. I think you can also compare it to this estimates in a star algorithm. So this is really an estimate of the cost that you still get, but then it's not the cost, it's the heat. And so this heat, it is really different than just the cost of an edge, let's say, because it takes into account all this contextual information in the graph, like how is a node positioned with the other nodes, and then what are sensible edges, let's say, in a solution. And so this is designed obviously a bit, but in such a way that it can efficiently leverage these heat values, which can be efficiently computed by a neural network, because we can just predict this heat map at once. And then this is very efficient to compute, which is important because we need to do it in every step of our dynamic programming algorithm. We need to compute this for a lot of solutions. And using this definition, we can do that very efficiently. We can actually compute it incrementally, so in constant time, let's say. So that's very important because we can make this dynamic programming algorithm efficient. And so overall, that means that if we summarize the algorithm, we just start with the problem instance. So in this case, it's a TSP instance where we have a set of node coordinates, let's say. We input that into a graph neural network, and this is then going to predict the heat map. And we're going to select, let's say, randomly a start node in this case. And then we're going to expand this solution in iterations. And at a certain point, we're going to group together solutions which correspond to the same dynamic programming state. And then we're going to remove dominated solutions. And so that sums up the overall algorithms. And so we conducted some experiments to actually test how effective this is. And so we didn't consider only the TSP problem, but also vehicle routing problem. So for this, we can also make a dynamic programming formulation. It's a bit more difficult because we have to take into account both demands and length considerations, and we also considered the TSP with time windows. So there's also that there's two dimensions. So there's the distance or the length, and there's the time aspect. But we can do this nicely in this dynamic programming frameworks. And so basically we can use the same method, but we train the model. We train a different model for each of the different problems, and we train this model based on example solutions that we compute up front using a different solver. And so if we're going to look at the results, so this is a big table with numbers, which I don't want you to look at all, but the point is that we compare to a lot of other methods which use machine learning-based approaches for vehicle routing problems. And we are competitive in terms of, let's say, the gap we get to a state-of-the-art algorithm. And most of these works actually compare to LPH, which is a quite general heuristic solver for many vehicle routing problems, but we actually also compare against state-of-the-art hybrid genetic search algorithms. So this is why the numbers are maybe a bit higher than you see in other papers, because we used a different or stronger baseline, let's say. But we see that this is quite competitive in general, and it outperforms actually most of other approaches which use machine learning in their algorithm. So this is for the traveling salesman problem, for the vehicle routing problem. And so then also we considered TSP with time windows, which is actually quite interesting because of this time windows, the problem becomes actually much more restricted, because you can't always visit any nodes in sequence. And this is very convenient for a dynamic programming algorithm, which really constructs a solution in order. So if you have to respect time windows, it's very easy to just make sure that you respect this time windows. And so there we see that if we compare against some quite recent highly performant algorithm, or at least the best open source implementation we could find, that we can actually improve on the solutions that we get. Then one more study that we did is the trade-off basically between the running time and the computation. So what we can do is we can like make the size of the beam, so the number of solutions we consider in each iteration, we can make it bigger or smaller, and this then trades off the quality of the final solution found versus the overall runtime of the algorithm. And it's always a bit difficult how to compare, because our algorithm runs on a GPU, how we compare with the machine with CPUs, but we compare, let's say, some different options, and we see that roughly we get like comparable results if we compare with this LPH algorithm, which I think is a very reasonable comparison in the sense that it is quite a general algorithm like this dynamic programming framework. It's quite a general framework. So we're not claiming that we strictly outperform this, but this we will see in the next slide. Compared to classic dynamic programming algorithms for vehicle routing problems, we really improve a lot, and that, let's say, in this first try we can get competitive at least with this this other like highly engineered approaches. I think that's very encouraging for this this direction of research. Yes, so lastly, we also compared against this dynamic programming, let's say the classic dynamic programming algorithm. If you would just rank your solution based on the current cost, then you really see that you can get gaps up to like 20%. And by just using this heat map with the potential, we can really cut this down. And then we did a few ablations. So what if we don't use this potential? What if we don't use the dynamic program, but just the beam search? And we really see that all these components together, they make up for the performance. And this really makes quite a lot of difference compared to a classic dynamic programming algorithm.
Right.
So
well,
that,
yeah.
yes.
Okay. I'd like to ask you to shortly wrap up if possible.
Yes, definitely. I'm sorry, I'm a bit, but this is last slide. So this wraps up the algorithm. So it's a flexible framework. You can do this for many VRP variants. It's suitable for GPU implementation, and you can naturally trade off the computation and the performance. And it's even asymptotically optimal. So if you make the beam size larger, if you make it infinitely large, you will get the optimal solution because it's just a dynamic program. And you can train this model very efficiently using example solutions. And at test time, it's efficient because you only need to run your neural network once, which makes it efficient to implement it in this algorithm. So with that said, I would like to thank you very much for your attention. I'm not sure if we have time left for a question, but I'm always open to having discussions if you want to reach out to me.
Yeah, there's not a lot of time, but it would still be nice to have to see if there's some questions here in the audience, maybe. Yes, in front, you should speak.
Yeah, this is a question about a graph neural network part. So if I remember, it is a graph neural network on the induced graph by the k nearest neighbor. So I want to ask you about the effect of that k, because it sounds to me like it's almost always connecting the nodes that are close to each other. So wouldn't it be helpful to compare to a heuristic that does specifically that?
Could you hear that question?
Yes, I think the question is, what if instead of this heat map we use a heuristic which just considers k nearest neighbors?
No, I'm not.
Yeah, because I believe the graph that you run the graph neural network on is the k nearest neighbor induced graph from the metric TSP.
No, it's the fully connected graph. That's the input.
okay.
Basically.
Got it.
Yes.
But I would have the follow-up question, like, can't you just run any TSP algorithm on those heats on the output of the graph neural network?
Yes,
Did you
that's
try
a very
that?
good question. I think you can. I think this was also what you mentioned in your own presentation, right? Yes.
Indeed.
So that is true for TSP. I'm not sure if it holds for all the other variants, but that is definitely something interesting to try.
All right. Yeah, I think with that and with the interest of time, thank you very much, Wouter, for this nice presentation.
Yes, thanks very much for your attention.